if you want to just get a bottle, there's one. Okay, again. Yeah, go ahead. Woo-woo.
Am I good? Oh, okay. All right, just some quick announcements. Before I forget to mention this, because I forgot for the last two talks, the next talk about Blu-ray discs is unfortunately canceled. In its place, you will get a talk on quantum computing and using Python for quantum computing. If you were at the demo party last night, somebody showed off their slides for that. That is the talk you will see. So I'll post some more information on Discord about it. But yeah, unfortunately, that is canceled and swapped to the quantum computing backup talk. Later today at 5 o'clock in this room is closing remarks. So come give thanks to all the folks who volunteered and put time into this year. Pretty much all the contests are wrapping up right now. So if you're looking to purchase soldering Olympic boards or any kits or stuff from the various vendors, I'd probably get it now before they start packing up for the day. If there's anything else, come hit us up at registration. And then if nothing else, coming up next is SPECTRA, Semantic Pattern Extraction for Scalable Malware Detection.
Thank you. Thank you. Thank you.
Hello, everyone. Thank you. Thank you so much. Welcome, and thank you for coming to my talk about SPECTRA. My name is Mohsen. I'm a senior security researcher at Cisco at Thales team. So I think you probably hear about that. And then specifically on the threat research and efficacy. In today's talk, can I take this one? Okay, nice. So in today's talk, I want to go through SPECTRA, which stands for Semantic Pattern Extraction for Threat Research and Efficacy. In short terms, why this matters to the whole cybersecurity is that scaling, so basically like the malware detection is yet another similarity problem. So like similarity matching and similarity finding because of different variants of the malware. So, and every method that we use these days either like scales, but it is fragile, or it is robust, but it doesn't scale. So SPECTRA's attempt is to kind of bridge this gap and find that kind of middle ground, and because of this trade-off, and giving the analyst like a semantic representation of the binary that holds up across different variants and families of the malware. So just might be as a brief background about myself, and like basically since it shapes like how I came to this problem. I'm currently at Cisco Thales and focused on applying AI to program analysis and reverse engineering. Before that, I worked at Apple, Sear Laser team, part of platform architecture security, and I contributed to the development of the M1 CPU architecture, specifically on the security spec. And yeah, coming from the hardware-rooted background, and academically, I got my master's in computer science from Arizona State University, with focusing on cybersecurity, and MBA in entrepreneurship and on innovation from Harvard Business School. And also joined the DARPA and Department of Defense program. Like there's also a program related to Cyber Grand Challenge. We have been participating from the Shellfish team as part of the Mechafish team to create automated agents attacking the different systems, and also while exploiting, also patching themselves, like automatic programming repair per se, back in 2017. So AI was not like this right now. And I'm a CTF fanatic and also a open source fanatic. And yeah, played a couple of CTFs like DEFCON, one of them. And Binlex is one of the projects that we're going to talk about. It's one of the open source contributions that I had. Cool. So coming to the background, again, why this really matters. Malware similarity refers again to measuring how close two samples are related to each other, like from both semantically and syntactically, and across different abstractions for sure. There are different ways currently in the market, starting from the byte level. So we compare the raw bytes of two samples, and this is like highly fragile, as you could tell. And micro changes to the code base or even to the assembly will break this similarity. The other one is the structural based, which is the we analyze the control flow graph and data flow graph of a program, but still this can be altered because of the different transformations and compiler transformations for sure. Like a control flow flattening simply can break this one, and other transformations like inlining. The other one is the API level that basically works on top of a trace of an API, like, and also including the strings, imports, and exports of that particular sample. But I mean, you can tell that with stripping the binary, this is not going to work. And there are other features that we're going to talk about the semantic similarity that focuses on what actually code does by focusing on extracting the genome of a binary, like a genetic extraction. So working as part of like Cisco, so we are in work with team that creates the Metis, and like how we are expanding the Metis to expand toward not only the source level artifacts analysis using AI, but also on the binary side. How we can make Metis to work actually on the binaries in the wild, decompile those, decompose them, and find vulnerabilities within those. So this research kind of contributes to those stuff, to those models. So the real operational need is that in real world operations, malware is not just analyzed as just one particular sample. The way we analyze that one at a scale, because we receive through our threat grid sandbox, we receive millions or sometimes zillions of samples every day. So we treat them as what's the strain of this sample, what's this family, and thousands, like how, basically we analyze this one across thousands slightly modified samples, and each variant may differ. Like we have Deridex, and also TrickBot. Each of them, even sometimes they might be some of the groups working with each other, like a Russian group selling some portion of their encryptor to, or a C2 kind of server to another group. How we can find that? It's very important for us as part of we are doing this one, because it's about the state-sponsored attackers sharing the tool sets with each other. So that creates an operational problem that traditional signature-based or exact matching detection does not scale. So in today's kind of binary similarity, as we talked about the byte level comparisons, we have algorithms like MD5. I mean, you heard about that. It's just considered to be secure cryptographic hashing algorithm. And also we have many to one hashing algorithms like the one that called ITIS. And also I think it's LSTH, yes, so that's used by VirusTotal to find the similarities. So all these are extremely fast and scalable, yet fragile. As mentioned, minor changes will break the whole scenario.
Yeah.
The other one is a feature-based that they basically capture like the histograms, n-grams, or byte similarities from like the different samples. And again, this one with simple code cave tricks can be bypassed. And the other one is the structural, like the CFG control flow based kind of detections. And examples of that one is graph isomorphism, or some other mechanisms to find the similarities between those, like cosine similarity, Euclidean similarities. And there are some other highly advanced techniques and tricks like symbolic execution. Like if you have heard about Anger, as they do symbolic execution on the code base, and I was one of the developers working on that. They work on value set analysis and also the symbolic traces and also concolic traces. But you can tell that when you try to trace, you hit the roadblock of sandbox detection. And then if your sandbox is not immune enough, you cannot just basically analyze the sample. So there are different levels of obfuscation techniques that can prevent that. And the behavioral or telemetry-based operations, like you get the API trace as mentioned, you use the long-term, short-term memory, LSTM, for anomaly detection. And again, that one can be bypassed because there might be some sort of time delay attacks happening, or trigger-based malwares that on a specific trigger, they are waiting to hear a specific event and then they will be activated. So that way, these kind of methods is not working. And the place that SPECTRA is kind of targets the middle of these ones. So we are not going too much into the graph neural nets or GNNs to be kind of attacked, and also too much into like the symbolic execution because of the path explosion attack. I mean, like not the attack, just path explosion problem. And also, if we are too much on the structural side, they can bypass us using the control flow flattening and those transformations. So yeah, putting all these together, as mentioned, so all of these methods, specifically, like as you can see on this screen, they have their own strengths and also their own limitations. Like picking just one of them might be the graph neural networks. You can see like the limitation and strengths is just, it's very good. Like with the ML techniques, some of these methods are very good with very ML friendly. We have been looking for something that is also machine learning friendly, AI friendly, because if it is not, so we cannot scale. That's why SPECTRA kind of sits in the middle of the decision making and of between having four different criteria within this problem. So scalability, that we need to compare the samples against a corpus of millions in seconds, not even hours. So that immediately rules out anything that is path explosion related to the traces or dynamic execution or DBIs. Yeah. So being also deterministic, the same binary should always produce the same representation over and over. Same equivalent variant should produce the same exact whatever hash or whatever vector that we create or representation. And being architecture agnostic, most of these byte level scenarios that we mentioned are not agnostic because different compilation tricks like O1, O0, O7 can change like the whole inlining, like the instruction sets, and also cross compilation for the malware samples. These days, a malware author tries to cross compile across different architectures like x86 to ARM, MIPSEL, and RISC, and some others. Yeah. And also being ML friendly, as mentioned, because if the output is not like a vector and that vector does not represent the proper embedding and the distance features, we cannot use that one for the clustering. It's like a clustering similarity kind of problem. So considering all of them in place, we created SPECTRA with the idea of a binary genome. So we are creating a genome of the whole binary, and we lift this code to a normalized intermediate representation because of maintaining like an architecture agnostic view. That intermediate representation, we're going to later talk about that, but it was VEX as the winner of that IR, not LLVM for certain reasons. So we abstract away all the low-level behaviors using these IR operations, and we capture the data flow and also control flow at the same place. And then we add some higher level context like API call graph, a string semantics, and also like some of the, control flow graph, call flow graph, data flow graph, all these things, which shows the intra and intra procedural analysis and dependency and interdependence between different constructs of the binary. And strings, for sure, if the strings are available. If not, I mean, we don't care if it is stripped. And then operations like arithmetic operations, bitwise operations, and all these things are captured within. So you might ask why we chose an IR and also why we chose VEX specifically, because there are popular IRs like LLVM. So VEX is designed for lifting raw binaries, and meaning it can directly translate the code into a normalized IR without requiring the source level assumptions, while LLVM sometimes requires those source level kind of assumptions. And the second is that VEX provides a very low level kind of semantic. As you can see, every instruction is broken down into simple operations like register access, registry access, memory access, store loads, arithmetic operations. Even that you see that one assembly instruction like return, that's the LLVM IR equivalent, and the other one is the VEX IR. The vex IR captures more semantic info from just that one simple instruction, which means that not only for this particular research, but back in the time in Apple, we have been working on CPU, you need to kind of emulate the microarchitecture of the CPU and the things happening as exactly like that one instruction. What are all the artifacts that one instruction has over the CPU states, over the machine states? Yeah. So we are capturing all of that here using Vex. So Vex coming from Valgrind project and this LLVM. I mean, we all know about that, I guess. So speaking of the IR-based vector embeddings and creating a vector, so all we are doing here at the end of the day, we're going to have a very good fine-tuned vector, yeah, to basically pass this on to conventional AI and ML models. So we start with the assembly instruction, which is architecture specific and quite noisy. And then we lift them to a Vex IR with some normalizations. Vex is a RISC-like kind of representation for operations. You saw that we have the registry access, memory access, all those fancy stuff. And each IR instruction, then it is mapped to a semantic category. That's the IR category you see on the third section. Means that these are like the registry access or memory access or stores or arithmetic operations. And then we count how many times we saw each of those vectors, and we put it over the vector, and finally we normalize the vector over the course of whole operations happen in this basic block. So that's just to give an idea about the normalization. It's definitely complex than this, but just an idea. Yeah. So we start with the binary, and then we use Ghidra, and we lift the raw binary into a structured binary context. We called it BCC. And that contains the key elements and artifacts that we need for analysis. Contains like functions, basic blocks, instructions, strings, and imports, and even more. And then the context is then serialized to a protobuf format. And then we finally encode that protobuf format to a TLV. So this TLV is like type length value segment. And that's the way just to represent these stuff, these structs, because we want to find them somehow. So type, I mean, name implies, what does that mean? Type, and then the length of the coming bytes and the actual bytes. And then we finally hash those for the purpose of integrity of these constructs that we are creating, making sure, nobody's running again and, modifying the stuff and we don't know what we are dealing with. And then finally, And then finally, we compress the whole thing. And then that's like the whole structure of the BCC. So in the next slide, I'm going to cover exactly what these two constructs mean, because we have only two types. We are not overcomplicating this whole thing. Every artifact, as mentioned, wrapped into a TLV envelope. And that TLV envelope, like as a type, has two types. So one of them is the binary context record that represents the entire binary as a system, as a framework, as an OS. And the type byte is like 0, 1. And then the length tells us like how many bytes it will follow. And then the value contains like the metadata of the file, like the architecture of the binary. If it's a PE, like the header of the PE for sure, import, exports, string references if there is anything available, and disassembler level insights from Ghidra, any decompilation. So you see we are capturing different features here, but we're not going to use all of these features. Some of them are going to be noisy. We need to redact the noises. The same happens for the function. So a binary consisted of different functions. Functions consisted of different basic blocks. Yeah. So we go one step deeper. Under the function, we have basic blocks, instructions, and also the boundaries, like the function boundaries and all these things. So now we are coming to one of the problems in reverse engineering and applying AI to the reverse engineering. And one of these conventional and first challenges is the tokenization. So which means like breaking down the compact binary identifiers like, for example, in this case, set resource UID or set res UID into some meaningful components. So if I ask you, and if you haven't done any sort of Linux, like syscall, like programming, anything like that, this might be a little bit bizarre to you. What does that mean? So these strings don't have any delimiters, as an example. No space, no underscore, no camel case, anything like that. So just a blurb of characters. So how do we split them? So that's a real Linux syscall. And a naive and greedy approach here is that we first match it using like some of the dictionary words, like keywords in the dictionary, as human wrote those dictionaries. And then this greedy approach means that it might split the things like SE TRES UID or set RE SUID and different constructs. But which one is the correct one? So we know that it's about the set resource UID, and that's how it brings some level of meaning to the whole context. But it cannot effectively capture that one. And that's one of the main issues in the stage one, which is the like conventional greedy like pattern matching. Then we go to the probabilistic approach. So we explore the probabilistic segmentation using Word Ninja. So you might have heard about the Word2Vec and all these like fancy names, but you know what actually is beneath that is they all leverage the Zipf's law. So, and Zipf's law tells us that in any natural language corpus, the frequency of a word is inversely proportional to its rank. So the frequency of each word is inversely proportional to its rank. So common words are quite very common, like THE in English, and rare words are also rare. Okay, so that observation gives us a powerful way to score the candidate splits. So how we use that in the binary analysis, because it's not a human word, yeah, like SE or set, yeah. So we need to build a vocabulary rank by the frequency first. So each word gets its own score, and common words getting higher score, and like rare words score low. Then we enumerate every possible like juxtaposition or possible split of the input using the dynamic programming. So means that for set resource UID, we might get SE TRES UID, and then or even set res UID and different things, yeah, and so on and so forth. So, and we score each of these splits with the log of the probabilities, like logarithmic of the probabilities. And we multiply. So how we do that? We basically multiply the individual word probabilities, and we sum the logs for each split that we had, and we pick the most kind of likely segmentation based on that dictionary that we had. And this will ensure us that we find a global optimum rather than falling into a local greedy one that, in the previous method usually fall into that local greedy one. So it will find us like a more kind of optimal solution. So, but still, like Word Ninja, it returns like set res UID for us. However, what you're gonna do with fork, like fork in our terms doesn't mean like fork, like I've been at ASU, so like pitchfork or stuff like that. So it means that process, it's about like the context of the process. So in this particular case, that's the limitation of Word Ninja. Yep. So it is limited by the vocabulary that it has been trained on. So to address the Word Ninja's vocabulary limitation, we trained a custom Word2Vec model on a corpus of reverse engineering artifacts. So function names, symbols, the compiler output, call graphs from the real actual binary samples. And this model, by the way, is publicly accessible. So it's under my GitHub, so you can take a look at that and use for the research. And why custom? Because as mentioned, general purpose dictionaries do not know terms like malloc or fork or memcopy or execv and ptrace, get PID, get UID, and things like that. So these are everyday vocabularies of a reverse engineer guy, but invisible to the standard NLP corpora. So we train the word2vec directly on these reverse engineering artifacts. And based on that, so now it can without even we do anything further, just a simple training, it can now find the context that malloc is related to memory, heap, and alloc, or even fork is related to the process, thread, and execution. So open is related to the file descriptors, read, writes, and things like that. These are like all the similar things within that context. And that what matters, yeah? So what matters most so even like, let's say Metis wants to go and analyze something. If they don't have this context, they work based on the context, they will be lost. So that's how we augment that tool to make sure it can find the similarities, it can find the context and follow the context along. So, and then we focus right now on how we convert the tokenized binary strings into embeddings. As you can see, so we have a simple averaging approach on the left side that things like allocate, memory, or syscalls contributes equally to the final embedding. While this is easy to implement, but it treats very common words like on or failed the same as more meaningful technical terms that we have. So it doesn't bring us value. So you can see like the more important words, I kind of try to highlight them with color white, and the other one is a little bit gray. But right now it's all being treated the same way. On the right-hand side, we improve this one using the inverse frequency weighting. So here we basically assign the lower weights to the common tokens and also the higher weights to the rare ones. So that's, when you do reversing like on a daily basis, you are looking for things that are interesting. So basically I'm trying to mimic the way that we as humans think, and we need to translate this stuff to a machine. Yeah. So these are like those very simple things that AI researchers do that makes these LLMs work. Like by just iterating the way a human works, even at the level of the neural nets, the same applies. So here a reverse engineer looks for interesting strings in Ghidra or IDA or, strings even, yeah, to start your exploration from those interesting things, not the common ones. If a library is already compiled within that thing, you can find that, oh, these are the library stuff. I shouldn't completely focus on these. There are more interesting stuff there. So that's how I'm trying to kind of represent that one and make sure that with this new frequency in place, that common words are not getting that amount of attention by the neural nets than the rare ones. So we prevent the dilution of the informative signals that we have. And then the common words are, getting less attention, and rare ones getting more attention. Coming back to the paper of attention is all you need. So basically that's about the baseline of the embedding. So I'm going to close this one here. And here we go to the inverse frequency weighting. So on this slide, we fix the problem with inverse frequency weighting. So we start by measuring the corpus frequency across our reverse engineering corpus. On appears, as you can see, like 10,000 times, and failed like 4,000, memory is about 2,000. And then we notice the inversion of importance. The rare technical tokens like syscall and allocate are exactly the ones that carrying the most amount of information and signal for our AI. So common boilerplates like on or failed is a noise for us. So we compute the weight as log of the n divided by frequency, so inverse frequency, and essentially the inverse the document frequency, like TF-IDF kind of format, coming from that mindset. So lower frequency means that higher weight. And then that's how on this side, we can see that allocate right now gets more importance compared to like on or fail that we had. Cool. So now coming to the binary ranking. So binary ranking is about identifying what parts of the binary matters most, where to focus. So we start at the function level where we build a call graph and estimating like how frequently each of these functions is being visited. Like for example, a main function has been visited the most, yeah? So that gives us a global importance score across the binary. So then next we go deeper into each function by analyzing the basic blocks that constructs that function and it constructs the control flow. And we weight those basic blocks based on the importance of their parent function, and also aggregating the scores to identify the critical execution paths into that execution path basically. And finally, we move to the string if it's available, and we link the strings to those basic blocks and we reference them to maintain the context. Again, we are trying to link the context as much as possible. So when you are trying to tell AI to do something, it exactly knows what we are referring to. It has all the information in one place. And then, so for example, error messages, common execution like paths or network activities, we just try to basically capture those. You see like socket, get, bnsh, those kind of strings, we also put it like near each other. So overall, we move from a structure right now to behavior. That's how we bridge the gap. Yeah, that's a very important slide. So from the functions to execution paths to semantic signals, and enabling the better analysis for malware detection, API discovery, or even if you guys are into fuzzing or finding vulnerabilities, because which parts of the program are more interesting to go and have the AI to explore. It's like exploration strategies you can come up with, and also reverse engineering. So basically, an example, let's walk through one of these like ranking a cascade on a concrete example. So imagine a small binary with several functions like main, init, like parse, run, log, and a lot of others. I'm not sure you can see those dotted lines because I cannot see. You can see that dotted lines here. Okay, cool. Thank you. So we want to basically understand from this call graph that we built and computing the visitation frequency, how often each function is reached from the main during the typical execution. And so main, as you can see, itself gets about like, I think 10%, and it is a top rank function and visited almost on every run. And then exec and the others. So the hot functions are visually highlighted in cyan, and like init and the rarely called helpers faded to gray. So here, basically the top rank badge is main, yeah? So now we zoom inside the main, and now we look into the CFG and the constructs of the basic block, like the control flow graph of the main. So basic blocks, yeah. So the constructions of this function is based on basic blocks here. Basic block 1 is the entry, and then basic block 2 sets up the syscall, and then it branches. And basic block 3 then handles a log path, and finally basic block 4 handles an execution path. And then they merge as part of like a decision or something to that exit. I mean, not a decision, just exit of the function, like return basically. So basic block 2 sits almost on every single path through main. And that means it inherits the highest aggregated rank. Yep. So 6% in basically this illustration. And basic block 2 is highlighted in amber because it's a critical block. So finally, we take a look at the strings as mentioned, and that basic block 2 references, because basic block 2 is that hotspot. Yep. And then we have like bnsh for command execution, like, errors, like error messages, and also like the socket, like the network activity, API endpoints, like, API auth, like for the, like a RPC call or even like an, API call basically. And these are exactly the type of behaviors that the malware has. And now we are resurfacing these ones to the top. And we are basically using this ranking and embedding, we are resurfacing to the top. So that's the whole idea of this whole like presentation, like these past 2 slides, just bringing up the whole idea. So then we expose the real behavior not just a boilerplate. And yeah, this one comes to the final kind of the architecture of the Spectra and basically the last slide. So the embedding that you saw, that's open source, and it's part of a contribution to an open source project called Beanlex. The rest of the stuff that you guys see here is portion of the proprietary of the Cisco, which we cannot disclose. But over there, over that GitHub, you can go and take a look. My handle is Poundslinger. And yeah, I mean, if you want to stay in touch, I mean, definitely you can just send me a message or something over LinkedIn or Twitter. And but that's exactly how it happens. So let me go through this one. So we again start with the raw inputs like a PE, ELF, or Mako file, like for Mac OS. And then Beanlex, that open source tool or engine, basically goes through the VEX lifting, converting that native kind of machine code to the VEX IR. And then we do IR normalization to find those semantic equivalent classes like registry access, memory access, those transformations that we have been doing. And then we perform a feature extraction and pulling out the artifacts, and we will embed those. And then these features fed into what we call it the semantic genome vector, or SGV. And this captures 4 signal classes: IR semantic features, data flow, patterns, operation frequencies, all those things that we talked about. Yeah, it's just in one embedding. And just as simple as that one, this embedding is the genome vector that we build. Now, if you take a look at it from a function level, we put all these functions together. Now we have the whole binary, or even the whole firmware, as the whole. And we can now focus on different parts. So that's how we are finding the families of the similar malwares. For example, we can tell you that this one is coming from the APT29, this section, and they are borrowing and sharing the code bases with each other. So that's how this works. So as we are getting close to the end of the conversation, so thank you for your attention. And this is my you can find me on Twitter, on LinkedIn using the Poundslinger. And if you are open to the collaborations, definitely send us a PR. We are open to new ideas. And yeah, thank you so much for your attention. Any questions?
Yeah, no, really, just the yell.
Yep.
Maybe the phone, the fucking creative read, something because if that's not typing yours, you have a bad now.
Very good question. So because we don't want to go through the hard. Oh yeah, for sure. Yeah. So basically, the question is that under the function visitation, you're asking if this one has been done through the dynamic traces of a program, or statically we are capturing those. So right now we are just using a fast CFG pass. So fast CFG pass means that we just go statically over the whole function, the whole program. So we are not trying to go through the dips and downs of the symbolic execution, or even the runtime operations, which means if you have the virtual functions like in C++ per se, we are kind of lost on that side. And that's, again, about the pros and cons that, comes to the slide that we had, what we are choosing. Yeah. So is this a combination between you're choosing the high abstraction or low abstraction, the speed and depth. So that's the kind of, we are trying to balance between these two. But you are right. So if you have the computational power on the server side to do more analysis, which actually some of our engine does for certain APTs, we go to that depth. But for this Spectra, we are trying to kind of stay in the middle. Thank you.
No, no, that's bad.
Yeah.
For the works, great second phase, kind of was the I guess if I get involved with things right now, block trying with live results.
Yeah, for sure. So the question is that regarding the segmentation of the strings basically and finding the right segments. Why we are doing that one? Because if you look at the segmentation slide specifically on this one, if we don't find the proper segments, we don't know what are the bag of words close to that particular basically, like in this case, syscall. So if you don't find that bag of word, so we cannot specifically find what it does. So right now, when we do that one, if there is a malloc, for example, it already knows it's doing something with memory and allocation, just to put all this stuff near each other. So we are trying to put information as much as possible close to each other, so to maintain the context. So it makes the AI or ML find the things faster, like using the proximity metrics. And that's exactly the same metric that is applied in different areas of the system. So proximity on this one, and also proximity on the malware families on the large side. Yeah. So every little section of this whole piecing together about like the similarities, either is like as simple as a cosine similarity or might be like more advanced similarities. But having these, capturing those and finding those, how close they are together, it can help us with the context that was missing from this whole reverse engineering side.
Yes, that's that what like aren't you fixed in Braille for the second is yeah.
So are we constructing the fixed engrams or no? It might be segmented later on. So as we evolve so with the first word2vec, we have been just relying on the conventional vocabularies, yeah. And then after we trained on a better data set, it improved significantly and actually helped us to find kind of more granular kind of patterns. So we are consistently updating that one to make sure we are capturing like cross different compiler dialects and like different things, with the focus on being on an IR level for sure. Because if we lose that IR level, we're not gonna be architecture agnostic. We are trying to make sure this is working across different platforms, and already Vex supports like the cross-platform operation for us. Thank you so much for questions. That was very good. Any other questions? Okay, seems nothing. Cool. Thank you. Appreciate it. Thank you.